Hi, this is Dr. Justin Essery. This is week one of Poli-Sci 506, Bayesian Computational and Nonparametric Statistics. And I want to kick off the first lecture video by talking a bit about why it is that you might be taking this class, why it is that we're interested in Bayesian and nonparametric models, and then transition into a discussion of model fit, assessment, and comparison. And you might ask yourself, well, why aren't we talking about Bayesian models or nonparametric models on the first day of a Bayesian or nonparametric models class? Why are we talking about model fit assessment and model quality? Well, the reason for that is that Bayesian and nonparametric models exist for many reasons, but one of the reasons they exist is because there are certain things that structural models, like generalized linear models that you learned about in your previous classes, don't do as well. So I've got my first question here is, why aren't GLM models the only game in town? Why do we have this class? Why don't we just continue to expand on the GLM framework? And of course, there's the funny answer of, well, statisticians need careers, and so got to do something. Might as well invent a Bayesian model. But the real reason is that structural models include a structure. And I've got a little equation here. It's not really meant to be a real equation. It's more like a heuristic. But the idea is that an inference you derive or you draw from a structural model like a GLM model, any information you get out of that model is composed of two parts. A part that comes out of the data set and a part that comes out of the assumptions that went into constructing the model. Now, there's nothing wrong with that. In fact, adding assumptions to a model can be extremely useful if those assumptions are a good representation of the underlying DGP, data generating process. But in political science and in many fields of social science, or even in just the regular sciences, not every situation, not every data set, not every structure is well matched by a GLM family or some other structural family model. And Bayesian and nonparametric models are adaptable. They're fundamental. One of the fundamental advantages they have is that they can be adapted. Oops, I spelled it wrong. They can be adapted to a variety of different frameworks with comparative ease. And that's basically one of the things we're going to be talking about for the rest of the semester is different situations where a Bayesian or a nonparametric model is something that would be very helpful, that would allow you to do something you can't do with a structural model, or allow you to draw a more accurate inference than a structural model would. And I've just noted a few examples of where this can happen. I want to start off talking about this example, the example of unit heterogeneity. Unit heterogeneity is a case where, as you learned probably in your previous courses, not all of the units in your data set are perfectly substitutable for one another. Some of them are more like each other than others. So for example, if you have country level data, if you have data from country years, lots of different countries over lots of different years, it's not surprising to find, for example, that all of the German observations are more like each other than they are like the Italian observations. All the Italian observations are more like each other than they are in the U.S. Observations. That's not at all surprising. Another example in the American context, if you've got presidential election polling data, it's not surprising to find you got U.S. Everyone lives in the United States if it's a U.S. polling data set, but then different people live in different states, and all the people from Alabama are likely to be more like each other than the people from Mississippi, and so on. And then inside of those states, there are different counties, and so you might expect to see these structures like this. And so in cases like this, where you have different units that are more like each other than they are like others, and in cases where this structure is relevant to the model, so that is to say, these similarities and differences bear on the relationship between an independent variable and a dependent variable that we care about, then you want to do something about that. Now, there are lots of solutions in the GLM framework for simple forms of unit heterogeneity. You may remember the random effects model or the fixed effects model. These are general approaches to the problem that make sense. But sometimes these forms of unit heterogeneity can get very complicated. For example, not all forms of unit heterogeneity are nicely nested, like in my example here. We can easily think about this in the case of presidential elections. There are structures of presidential, of voters, hierarchies of voter similarity that don't map inside of one another. So for an example of a non-nested hierarchy, for example, we might have similarities among religious groupings or racial groupings, and we wouldn't expect those sorts of similarities to necessarily be nested inside of other sorts of similarities like state or county similarities. For example, it's not the case that all the Baptists live in a particular state or all the Hispanics live in a particular state. And so if you want that kind of non-nested hierarchical relationship among your units, you're going to have to start to think about a pretty complicated model. Bayesian and nonparametrics techniques allow us to think about that kind of complicated nesting. Another example I've got listed here is nonlinearity in response. Now, a lot of the structural models, the GLM models like Poisson models or logit models, are designed to account for certain kinds of nonlinearity. So for example, a logit model allows us to deal with binary dependent variables where the relationships are in some way not linear. But there are other kinds of nonlinearity. We're going to talk about some of them today. So for example, you may see a relationship between y and x that looks like this. What do you do with that? Well, we can think about maybe doing some kind of polynomial linear fit. You might say, oh, y can be modeled as a function of x and x squared and x cubed and so on. But it might be easier to just fit a model that's designed from the very start to be more locally adaptive, to sort of adjust to the peculiarities of the data and not try to force things into, like for example, a linear regression format, which fundamentally wants to draw lines. We can use polynomials to make it do stuff other than that, to draw stuff other than lines, but at the end of the day, it kind of wants to draw lines. So nonparametrics give us a tool to think about dealing with that, and there are lots of cases where we might think about doing that. Finally, interactivity and conditionality in response. This is a topic that's been pretty popular in political science lately. I've written a couple of papers about it. I'm writing a couple more papers about it. And there are ways of adapting linear models to this format. But there are other approaches as well. For example, if we're really not sure about the underlying data generating process, and we expect that there's lots of interactivity in the DGP, and we really don't have a hope of capturing that, we might instead want to design a model that gives us inferences that are robust to lots of unknown issues and complexities in the underlying DGP. And so later on, much later in the course, we're going to talk about causal modeling or matching models. These models are designed to allow us to recover accurate inferences about certain important quantities like the average treatment effect in the face of lots of interactivity, conditionality in the relationship between x and y. They're designed to, in effect, purify or purge those conditionalities out and allow us to recover what we're interested in, some quantity we're interested in, like an average treatment effect. Matching models are fundamentally semi-parametric or non-parametric models. They're not really linear models. So as I hope you'll see, there are lots of things that you can do with, and this is just a very, very short menu of things, problems that you can attack with Bayesian and non-parametric models. What this all suggests, though, is the first thing we need to talk about is what some of these problems are with GLM and other kind of structural models and how you might detect those. And there are a couple of things that we're going to talk about. And what I want to do now is transition into talking about two different motivating questions that one might ask when assessing models' fit or quality. So like I said, there are two things you might ask when you're trying to assess a particular model. One is, generally speaking, in this particular data set I have, is my model doing a good job? And obviously what we mean by a good job is highly dependent on what exactly we're doing. So I've given a couple of instances or a couple of examples of what it might mean to do a good job in a particular data set. So one thing I've put here is it a good fit? Which is to say, is the model I've estimated capable of recovering information in sample? Are its predictions in sample a good match to what we actually see in that sample? A related, not exactly the same, but a related question is, suppose I've got a bunch of different models that I'm thinking about using on a particular data set. Which one is the best choice? Which one is the best fit? And again, the best choice can depend on what exactly we're talking about, what criterion we're assessing. But in this case, I'm focusing on the issue of fit. Which one does a best job of recovering the in-sample relationships in your particular data set? And then a little bit of a detour, but a worthy topic to look at nonetheless is how robust is my particular model to minor changes in the sample. So is it the case that if I delete one observation or change one bit of my data set that my results are completely different? This is a little bit of a diversion, but I thought it was worth exploring. Nonetheless, it's a pretty quick topic to cover, at least in terms of its basics. A second question, which is very different than that first question, is, in general, in these situations, is my particular estimator a good choice for this kind of data set? So on the top here, I've really got something like, is my linear model a good fit for this particular experimental data set or something? That's the kind of question I'm contemplating in this first bit. The kind of question I'm contemplating in this second bit is something more akin to, is it okay to use a particular sort of model, like a linear model, in this situation? Or maybe something like, how does my estimator, like an OLS regression, perform under these circumstances? Now that's a really different question, and it gets to the heart of some of the things I was talking about in the previous section. So for example, when you have these really complicated hierarchical relationships among your data where, like, all of the people in a particular county all have similar views, similar background, and that influences, that makes them similar in ways that are relevant to our analysis. What happens when we just throw an ordinary, vanilla, unadjusted linear regression at that problem? Does it blow up, or is it okay? That's really the kind of question I'm getting at with this second bit. And there are lots of questions we might ask, particular questions on this line. Something like, am I going to get the right beta coefficients, the right parameters, if I do this? And parameters are usually of secondary importance unless they happen to have substantive meaning. So really a more interesting question is, am I going to get the things I'm trying to estimate out of this model are those things going to come out right? So for example, if I want to know the relationship between y and x, the marginal relationship, the marginal effect between those two, is my particular estimator going to recover those relationships correctly in this situation? And we might also ask, okay, so suppose we know that the situation is not perfect. We know the situation is somewhat adverse. The model is not really designed for these circumstances. How bad is the problem? There are some times when problems just really aren't really that bad. For example, lots of cases of heteroscedasticity are the typical figure I've often heard cited is that robust standard errors are designed to correct heteroscedasticity, but usually they're within about 10% of the normal standard errors. And a 10% difference in standard errors it's something, but it's not huge. It's on the on the margin of whether a decision is really meaningful. But then there are other cases where changing models can completely flip your results or make them totally different, because the original model you're using is biased or in some way inaccurate. And so it might be nice to know, what happens when we try to do something a little off the wall. Is it okay or is it not okay? So the first question is asking, that blue question is asking us, the blue ink question up here, is asking us to assess the performance of a particular model, which is an estimator like regression analysis or like a logit, and a data set. So a model, in my little terminology here, is an estimator plus a sample. The first question is, how is my model doing? The second question is, how is my estimator doing? How good of an estimator is this? So for example, we might have an estimator which is in general good in a lot of different circumstances, but for various peculiar reasons is not really working in this particular data set for a variety of reasons. Maybe it's a bad match to this particular data generating process. There are two different things, and we're going to talk about both of them today. I really want to focus attention on that second question because as we explore Bayesian and nonparametric statistics, one of the things I'm going to often talk about is how and why Bayesian and nonparametric estimators improve in this second sense, in the estimator sense, on more basic structural GLM type models. All right, so what do I mean when I say, we want to think about whether a model fits inside of a particular sample? Well, there are lots of different ways we could conceive intellectually of assessing model fit. And in fact, later on in the course, we're going to read a paper that I just wrote sort of on this topic about logit models, where asking different questions about how a logit model is doing gives you pretty different answers because the questions are different. There are different ways of thinking about how a model fits. Let me just give you one real basic example of how our perception of model fit might change. So if I'm working for a government agency and they want me to do something like predict terrorist events, okay? I could think about predicting terrorist events with some kind of data set, some big model I build. And then I want to ask, well, how well am I doing? How well is this model actually performing inside of the sample of, if I was going to use my model to predict events that already happened, how well would I do? It might be much more important for me to avoid false negatives than false positives in that scenario. So the government getting a warning that, hey, there's a chance of a terrorist event happening on such and such a day, that might be less catastrophic than saying, nope, no risk of terrorism today, and then having an event occur. If that's the way you're thinking about the problem, then you're going to assess model fit much differently than if you say false negatives and false positives are equally weighted. Or even in the usual case in statistical methodology is false positives are really to be avoided, right? So this is why we have a t-statistic that is designed to produce 5% false positives, because we don't want to discover a bunch of relationships that aren't really there and waste our time, and waste scientists' time, graduate students' time trying to throw out all these garbage relationships. that's really, that's a much different decision criterion than saying, oh, false negatives, whatever, it is not even really that important. False positives is what we really want to avoid. So, that way of thinking kind of leads you down a pathway to statistical decision theory, which unfortunately we're not really going to get into much in this course, although it's a really interesting topic, and I hope that you get a chance to look at it at some time. But I just want to sort of put a bee in your bonnet to think about. There are different ways of assessing whether a model is any good. And when you're trying to think about that in your own research, you want to think about, what am I trying to do before you ask, how good is my model? Now, a lot of times, the question is really a little more basic than that. You're just trying to figure out, hey, I've got a bunch of points, scatter points in a data set, and I'm trying to make sure that the line I'm drawing through those points is not prima facie bad or ridiculous. And we have lots of informal techniques for doing exactly that. So, for example, if you've got a relationship between y and x, and you see your data looks like this, and you estimate a model, and the model says the relationship is that, well, you have some problems. You have some problems because, well, wait a minute, if you just look at this, I'm systematically overestimating all these observations, I'm systematically underestimating these observations, and these observations, probably I could do a better job than just drawing a line through it. These are basic assessment techniques that you can do without really any very much advanced training, and that are typically a part of introductory courses. So partially as a review, and just to illustrate how one would do these kind of diagnostic techniques in R, I've recalled the little data set that we worked with in the the very first introduction to R that we talked about last week. The data set's called gradhappy.dta. You can download it in this lecture file from the website and follow along in R if you like. And if we view this data set, you can see, just like we talked about last week, this is a fake data set that I created that has 3 variables in it. Graduate student happiness in terms of percentile from 0 to 1, number of years in school as a decimal, so if you've been in a year and a half, you have a 1.5, and stipend in thousands of dollars. So this person makes $20,833.36 and a third of a cent. And that's nice. That's what happens when you don't round properly. Anyway, so this is my data set. And as we talked about this week, last week in the first lecture, this data set holds some interesting characteristics. So if I just say, okay, I want to run a linear model between happiness and years in school. I want to see whether people get happier as they go through school, and I just run that model, I will find that, in fact, they do. In fact, there's a positive relationship between years and happiness, and every year I'm in school, I go up 12 percentile points. So I surpass 10% more of my graduate student cohort in happiness, because graduate school is just an unending parade of awesomeness. But if I do some basic diagnostics on this model, I can immediately see I have a problem. So what I'm going to do is I'm going to predict the fitted y-hat observations out of this model using the predict command and store them in a vector called pred. And then I'm going to plot the grad happy happiness object and the grad happy years object against each other. And as you can see, the plot just appeared here. There are some significant nonlinearities in this data set, and I just fitted a basic linear model to it. So we already know there's probably going to be some problems here. So what I want to do is draw a line that shows me what's my prediction line. What did my linear model tell me is the relationship between these two things. So what I'm going to do is use the order command to create an O object that just lists the order of from smallest to largest of the years object. So observation number 176 has the smallest value of years. That's a person who's been in just a couple of days. Observation number 37 has the long in the tooth graduate student who's been here for 5 or 6 years. So this allows me to draw lines in order. So what I'm going to do is use the lines command. The lines command adds a line to a pre-existing R plot. And I'm going to predict I'm going to draw a line predicting or depicting on the y-axis the fitted linear predictions that I just generated, and on the x-axis years. And I'm going to use that O command in order to put those observations in order so I get a nice straight line like that. Now, what happens if I don't use the O? Well, I can actually show you really quick what happens if you don't use the O. What happens is the observations won't be in order, and so you're going to get it's possible that you can get crazy sort of scribbling back and forth as I go from this point to this point to that point to this point. And in a linear model, it's not such a big deal because you're basically just drawing over and over and over again over the same line. But in a nonlinear model where you have curves, that moving back and forth along the surface causes the line to look really, really bad. So generally speaking, if you're drawing a line out of points, you want to put those points in order so you get a nice, good-looking plot. So I'm going to redo that. There we go. And, you know, I don't need a complicated model diagnostic to know this is not so good. I'm under-predicting lots of cases. I'm over-predicting cases. And I'm over-predicting them and under-predicting them in a way that's related to years. And as we know, correlation between the error and independent variable, or x, is bad news for inference. It implies that our inferences are not unbiased in the classical linear normal regression model. So I'm not going to do anything crazy. I'm just going to say, okay, well, how can I deal with this inside of the context of the linear model? Well, maybe what I'll do is I'll add a square term, because I know that adding polynomial terms to a model enables that line to, you know, look more curvy. In this case, I'm going to have years and years squared. That's going to allow me to draw a parabola. So I'm going to redraw everything, but I'm actually going to leave the plot as it is. I'm just going to add another line to it. I'm going to generate predictions out of a model with a square term, you can see right there, and then I'm going to draw the line with LTY equals 2. That is basically just going to make the line dotted instead of solid. So I'm going to be able to look on the same graph and see how my new model compares. And as you can see, it looks good. Looks a little better than before. Still not as good as it could be. I'm getting a little better at a little less under prediction or over prediction here, a little less under prediction over there, but I can probably do better. Well, let's just go nuts. Why don't we add a cube term, a fourth term, a fifth term, and a sixth term? We'll put in 6 polynomial terms and just see how it goes. So I'm going to do that, and now you can see in this dotted line right here, I'm doing a very good job of capturing the relationship between x and y with these polynomial terms. So this is a very basic fit assessment criterion, in-sample fit criterion, no complicated techniques or anything, and it's a good diagnostic. Of course, this is a little easier to do in this particular case because in this particular case we have just one independent variable, and so it's very easy for me to adapt things. As you're aware, this gets a little more complicated when you have more than one variable, but I'm going to show you a technique that allows you to draw these common sense looking scatter plots even in cases when you have more than one independent variable that's influencing y. But another simple thing you can do is instead of plotting x versus y, you can plot the residuals of the model versus the predictions of the model or against x. So for example, here I'm generating the residuals from that very first linear model, and then I'm plotting them against the predictions, and you can see this is not good. My y hat is correlated with my residuals. And in fact, if I add a plot to this, where I plot the residuals against grad happy underscore years, I'm going to find that those residuals are related to x as well. And like we just said, that is very, very bad news. But as I go to my more complicated model, I'm just going to skip to the 6th power model here. Now my residuals look very nice. This is x right here, grad happy years. This is the residuals. This looks like white noise. This is what residuals in a linear model, or really most models, are supposed to look like. There's no relationship between the predictor and x. So very basic in-sample diagnostic techniques. It's a good first cut, and it's definitely something you should think about when you're thinking about whether a model fits well in sample. Now what I want to talk about is how would you construct this kind of plot if you had more than one independent variable. And as you can see, there's some problems with, well, we'll just see what should we do in this situation. What are the problems with trying regular scatter plots, and what can we do about it? So as you might have guessed, the problem with doing basic scatter plots in cases where you have multiple independent variables that are all related to y, i.e. virtually all real data sets, is that those scatter plots can be misleading as a result of omitted variable bias and other versions of spurious relationships. We'll see an example of this in R in just a second. Added variable plots allow an analyst to examine the relationship between a DV and an IV, controlling for other variables in a model in exactly the same way that a linear regression or any other GLM type structural model recovers the relationship between y and x net of other causal variables z, or other well, not necessarily causal, just other correlated variables z. And I'll show you an example of how this works in just a second, but let me tell you first what the procedure is, and then get down to a sort of an applied view of how this works. So the way added variable plots are constructed, there are automated packages to do it and stated in R, but if you were going to do it manually, first you'd predict y using all the independent variables except x. So if I'm interested in the relationship between x and y, what I do is predict y using everything except x, and then save the residuals from that regression, or whatever model it is I'm using. Then I predict x using all the independent variables except x. So now I'm modeling x with everything except x, and then save the residuals from that. So, here's my candidate model. It's, I think y is a function of beta 0 plus beta 1 x plus beta 2 z, something like that. The first thing I'm going to do over here is I'm going to say, okay, I'm going to run this model and then save the residuals. Then I'm going to run this model. Actually, it's probably wrong to put betas in that case because they're not the same betas from the previous model. So I guess we could use alpha as alpha 0 plus alpha 2z. And then save the residuals from that model. So I've got residuals of y, and then I've got residuals of x. Then what I do is plot the residuals of y against the residuals of x. And as it turns out, there's an important theorem called the Frisch-Wall-Lavelle theorem, which you might cover in greater depth in a linear models class, which says that this procedure will recover the relationship between y and x that would have been recovered if I had just run this unified model. So in other words, this beta 1 right here from this sort of standard model is the same as the slope that I'll get modeling the residuals of y here against the residuals of x. So it enables me to see visually a relationship that I can get out of a linear model. And actually, sort of relatedly, the plot of the residuals against the residuals gives you a sense of what the data pattern actually looks like, not just the fitted slope, but the actual pattern of the data. So you can have that sort of visceral understanding of the relationships in your data set that you get from a scatter plot without giving up the control of omitted variable bias and spurious correlation that you get from running a true model. So let me show you how it is that you get this in R. There's a package. It's in the car library. So if you don't have the car library already, go ahead and install it. If you do, load it right now. And what I'm going to do is I'm going to remove all the stuff that I already had in memory, and I'm going to set the seed as 3294. Set seed is a command that tells R to basically move its random number generators to a certain point. Fun fact, R's random number generators are actually not random number generators, they're pseudo-random number generators. They are actually deterministic functions that merely look like randomness. And so if you set the seed of your random number generator to the same as mine right now, you'll get the exact same results I get, even if there are random numbers being generated, because we will generate the same random numbers. That's really important both for these demonstrative purposes where you can get the same results I get, but it's also important if you're running a Monte Carlo simulation, we'll talk about later, or doing some kind of computational work, so that people can replicate your results. You can show exactly how it is that you got what you got. So anyway, go ahead and set your C to 3294 so you get the same results I get. Then what I'm going to do is I'm going to draw an x and a z as variables, and I've drawn them in such a way that they're correlated negatively. In particular, x is negatively correlated with z. So big X means small z or very negative z, and conversely, small x or very negative x means positive z. Then I'm going to draw y out of a model, basic linear ordinary least squares regression model, 2x plus z plus 3 plus an error term, a normally distributed error term. Now, anyone who's studied statistics will know this is going to create a significant problem in terms of spurious correlation. The negative relationship between x and z is going to interfere with my ability to see the relationships between y and x and y and z separately. So for example, if I plot the relationship between y and z, I'll do that one first. I know there should be a positive relationship with slope equals 1 because I just made it so. I just generated that data. But looking at this scatter plot, it looks like there's no relationship at all. I would say there's no relationship, maybe even a slight downward relationship between the two. Why is that happening? Well, the reason why it's happening is because there's a positive relationship between x and y, and there's a negative relationship between x and z, and that passes through to this model. This is very basic spurious correlation that you might learn in a first statistics class. The same thing happens at a lesser degree if you look at the relationship between y and x. In this case, the slope should be about 2, and it's actually probably not that far off from 2. It might be something closer to 1 or 1.5. But the negative relationship between y and z is dragging down that relationship between y and x. So the question is, what do we do about that? How do we see scatter plots that make a little more sense? Well, what you do is implement this added variable plot procedure that I just showed you. And so what I'm going to do, whoa, that's not what I wanted. Stop now. What I'm going to do is run this GLM model. Now I have to run it as a GLM because the AV plots command in the car package wants you to run this as a GLM as opposed to an LM. But a GLM with no option specified is just a linear model fitted via maximum likelihood as opposed to ordinary least squares regression, matrix manipulation. So the results will be very close, and in large data sets indeed will be nearly indistinguishable. And then once I've done that, I just run this AV plots command and feed in the model object. And here's what I get. I'm going to expand this out so you can see it. I get a pair of scatter plots that show me the relationship between each independent variable and the dependent variable controlling for all the other variables in the model. So this is the relationship between x and y controlling for z. This is the relationship between z and y controlling for x. The first thing you'll notice is both these relationships are positive the way they're supposed to be. The second thing you'll notice is the slopes. This one slopes about 2, this one slopes about 1, exactly what they're supposed to be. So AV plots allow us to look at scatter plots of relationships controlling for spurious correlation, which is a really great thing. The greatest thing about it is it allows me to implement these simple diagnostics we just talked about even in very complicated models. I can construct AV plots for all the different variables and get a sense of, is one or two of my variables, is there a nonlinear relationship? Are there outliers? Are there problems, which we're going to discuss in a second? Are there other problems with my data that I can really get a sense of very quickly if I just look at the data set? Sometimes people don't use scatter plots in multivariate models because, spurious correlation is a problem, and so anything I see there is not really going to be that useful. Well, that's debatable, but AV plots answer that criticism by allowing you to explicitly control for spurious relationships with a statistical model that's appropriately designed. So diagnostic plots are a good idea, but we can also think about having a more formalized assessment of fit quality. Again, there are lots of different ways to think about this, and I'm going to focus in on one particular criterion for assessing fit, which is how well the model fits the data in the sense of deviation between prediction and observed values. So in other words, these formalized statistics are going to all fundamentally ask how good is the model at predicting its own sample, the sample from which it's estimated. So one way of getting here, and this is in the primarily comes out of the linear model framework, but also there are analogs in other frameworks, is the sum of squared errors. So this is the sum of squared differences between a model's prediction and the actual observed value of the dependent variable in the data set. So in a linear model, y hat, or the fitted value, is just x beta hat. If we were in a GLM model, we might have a link function g, and then we would have to pass x beta hat through that in order to get our fitted value of y. But either way, we get all those predictions, and then we sum up the squared deviations between the prediction and the observed value to get the sum of squared errors. The reason you square the errors is twofold. First, so that positive and negative errors don't cancel each other out when you add them together. Secondly, this has the effect of penalizing larger errors disproportionately. So smaller errors are downweighted relative to larger errors when you square them. The popular R-squared statistic is a straightforward function of the sum of squared errors. This is just the proportion of variance in a data set that's explainable via the model. And as you can see here, all it is just there's a ratio between the total variance in the data set, or the SST, which is just exactly what it sounds like, the sum of squared deviations between observations and the mean for the dependent variable in the sample, and the SSE, which is what's variance is left over once we extract the predicted variance using a model. So if you take that ratio, which is going to be somewhere between 0 and 1, and then subtract 1 from it, you get the proportion of variance that's explained by the model, or the R-squared. So the R-squared is the proportion of variance in Y explained by the model. And you can see why this is related most closely to standard linear models, because the variance of a binary y, for example, is not given by that denominator. You'd need to use a binomial formula for variance. So that's one way of thinking about model fit. Another way of thinking about model fit is through the likelihood, which you would definitely have seen many times before if you've taken a maximum likelihood course. So the likelihood, and this is an example for an OLS, or basic linear model, ordinary least squares regression model. The likelihood of a data set is just the joint probability of this data set, this particular sample, having been realized if the model were true. So it's joint probability of the data given the model. PR data given model. That's what the likelihood is. And just like any probability calculation, what we do is for multiple different, in this case, independent net of x events, we multiply together the probabilities to get the joint probability of all of them occurring together. So in a linear model, the error is normally distributed, which means that the probability of any particular data set, or of any particular observation being realized is just the normal probability, the probability from the normal density function of yi, given a mean of x beta hat, which is our fitted mean for this particular observation, given xi, which is the independent variable information for this observation, and a variance given by the VCV from the model. I'm sorry, not the VCV from the model, it's the standard deviation of the regression, which is right here. Here's the standard deviation of the regression. Times an n by n identity matrix. In other words, we are assuming homoscedasticity in the errors. Every error term has equal variance. If that's true, then they all have the same variance as the standard deviation of the regression. So hence, that should be the standard. That should be the standard error, or I'm sorry, that should be the variance for the distribution of any particular y. So in other words, drawing this out sort of visually, if you think of there being a y-axis here and an x-axis here, and we've got some data here, and then we fit a linear model to this, like that, we draw a model through it, what we're saying is that for any particular observation, if you know x, which we do, the distribution of y should be normal with mean 0, at least net of x means 0. So it's really mean of x beta, but once we've gotten rid of that, it's just 0. And a standard deviation given by the standard deviation of the regression. And if we move further up on x, the same thing is true. We've got a distribution around x that's still centered on the line. And so net of that line, it's mean 0, and the standard deviation should be the same. So the likelihood of all of these data points occurring together is just the joint probability of all of the PDFs for all of the observations. So again, taking a look at this data set, if we go down here and say, okay, here's a line, here's a particular data point, here's a data point, here's a data point. The probability of that particular, or the probability density of that particular observation occurring is going to be given by the PDF of the normal right at that point. The same is going to be true for this observation right here. That's a very unlikely observation, at least in this toy example. And actually, we can go up here, draw that in. There's the data point right there. So, and if we just multiply all these densities together, we get the joint likelihood of all of these things occurring. So that's what a likelihood function looks like, which you hopefully already knew from your earlier classes. And we could assess a model by saying, well, the model that produces the greatest data likelihood is ipso facto the best model. In other words, the model that is in some sense most consistent with this particular realization of the data, this particular sample, must be the best fitting model for this sample. You can do that with either one of these pathways. You can, for example, say the model that's the best is the one that has the lowest sum of squared error. In some senses, these two ways of assessing models are related. They're by no means equivalent, but they're related in spirit in the sense that both of them are fundamentally saying that the best model is the one that when you draw the fitted surface, the data points are closest to that fitted surface. The closer you can fit the points to the surface, the better the model is. But both of these fit statistic ideas have some very well-known problems associated with them. For one thing, they're susceptible to overfitting. I can, by this criterion, draw a perfect but very bad and dumb model of any relationship. So if I go here and I draw an x and a y, and I put in some data points, and then I say, I have a really well-fitting model, and here it is. That's my model. You can look at that and say, there's something kind of wrong with that model. And one way of thinking about that is, well, if I had new data that were realized, so if I just kept drawing from more and more samples of my data set, that model wouldn't be very good at predicting the new stuff. It'd be good at predicting the old stuff, but not the new stuff. So overfitting can be a significant problem with this approach, and we're going to expand on that idea in a little bit in a second. Also, it doesn't account for noise intrinsic to the data, and by that I mean there are some people that want to use R squared as a sort of universal statistic in the sense of saying something like the best model always has an R squared close to 1, and bad models always have R squareds that are tiny. That's not really necessarily true because there may be a lot of noise in a data set, for example, that makes it impossible to extract to explain a lot of the variance, because that variance is just attributable to random error. It's just noise. So I guess that what I want to say is that these statistics, even though they can be useful, can't necessarily be assessed in the way that one might want to assess them as universal indicators of model quality. At best, they can be comparative. We can say, well, a model that does a better job of fitting might be better than a model that does a worse job, although even there, we have to be aware of the possibility of overfitting and somehow adjust for that. And finally, likelihood statistics are really difficult to meaningfully interpret. A log likelihood, which is the usual thing that's being fitted in a maximum likelihood model, it's some number. It may have some kind of meaning, but it's very hard to explain what that meaning is relative to any data set. And so although a sum of squared errors is somewhat interpretable, a likelihood ratio statistic is a bit hard to wrap your head around and explain in terms of model fit. So what we're going to do is say, okay, these are our basic criteria for deciding whether a model fits a data set or not. How can we use these basic ideas but compensate for some of these problems that we're bringing up, overfitting, intrinsic noise, and meaningful comparisons? How can we maybe develop some formalized fit statistics that can overcome those, that get us beyond just saying the model with the highest R squared must be the best one, or the model with the highest likelihood must be the best one? So let's proceed and look at some of these different criteria. So we mentioned in the last section that overfitting can be a real problem when it comes to model assessment. So how do we deal with that? How do we deal with the problem of overfitting? Well, the question we're trying to figure out here, or they're trying to answer, is how do I know what the right level of fitting is? I want to reduce prediction error, or maybe I want to maximize likelihood with my model, but I don't want to do it so much that I'm literally just drawing lines between data points and saying it's good. So how do I deal with that? Well, one way of dealing with that is a technique called cross-validation, which is called the PRESS criterion in the readings from Nachter et al. That I assigned this week, or Kuttner et al., sorry. The idea between cross-validation is it's not fair in some sense for a model to get to use the information that it drew on to construct itself and then turn around and predict that same information. That's an easy task. A harder task is to take new information and predict that. So cross-validation, this is a particular version of cross-validation called leave one out cross-validation. And you'll figure out why in just a second. Leave one out cross-validation proceeds pretty much like this. I've got some data here and I've got some points, and I want to figure out how well my model fits, but I don't want to cheat and just sort of take my same data and then predict that data again. So what I'm going to do is I'm going to take an observation and I'm going to leave it out when I fit my model. So I leave that out and then I fit a linear regression to whatever's left. Then I use that model, which excludes this particular observation, to predict what that observation should be. So my y hat here would be that right there for this particular observation, and my error would be that little dotted line. And I came up with that prediction without actually using that observation. Now, if I've got a data set of size n, and I do this n times for all the different observations in the data set, and then I add up the squared errors, I get the cross-validation statistic. And this is called leave one out cross-validation because we're dropping one observation each time in order to fit the model. There are other kinds of cross-validation. We could drop 2, we could drop 10% of the data every time. There are lots of different ways we could possibly proceed, but this is one way, and I think it's a kind of an interesting way to proceed, so this is the way I'm showing you. The nice thing about this is there's no chance of overfitting because the model does not include the fitted observation. So I can't get away with just drawing lines between all the dots because the dot I'm actually trying to aim at won't be included. So it gives you a more accurate sense of how the model will perform in predicting out of sample. So what you would do if you wanted to use cross-validation to assess your model is just do this with every single one of your models and then choose the one with the lowest squared error that was produced out of this cross-validation process. The one downside is that cross-validation takes a lot of computational power. If I've got n data points, I've got to estimate n models plus the main model including all the observations. So I've got to estimate n plus 1 models. Now, if each model takes 0.2 of a second to estimate, that's not such a big deal. If it takes a week to estimate, like some really complicated models do, then cross-validation is pretty much not on the table. So let's figure out how this works in application. So I'm back in R here, and I want to let me expand this over here so we don't need the plot for a second. The first thing I'm going to show you is the R squared statistic and the sum of squared errors. What I'm going to do is just draw some data here, an x and a y. This is a basic linear model. And if I estimate regressions, well, the first procedure I'm using here is the GLM, the second is the linear model. You can see that these two procedures produce virtually identical results. I, in fact, cannot see any differences at all in these results. You'll see that, okay, x is related to y, just as we thought it was. The true coefficient is 2, and I'm recovering a coefficient of about 2. The intercept is 3. The true intercept is, or the recovered intercept is 2.89, so pretty close to, I'm sorry, 2.9. That's pretty close to 3, so doing okay there. And most importantly, the R squared, here it is right here, multiple R squared, is 76.81. So what we're learning here is I'm explaining 76.1% of, I'm sorry, 76.8% of the variance in this data set with the model. Now here's the problem. Suppose I just add in a bunch of completely irrelevant variables, z1 through z5. I'm just drawing junk data from -10 to 10 out of the uniform distribution. These have nothing to do with anything. They're complete junk variables. What happens if I draw these junk variables and then just toss them into my model? Well, none of them come up as statistically significant on their own, but on the other hand, they do improve the R squared. My R squared went from 76.81 to 77.19, which, if we're just using naive sum squared errors, tells us, hey, this is a better fitting model. Well, the problem is R squared, as you may have learned in your linear models course, is guaranteed to go up when including new variables. It weekly increases with the addition of irrelevant variables. The R squared can never go down, even when you're adding a completely irrelevant variable. It can only either stay the same or go up. So this can be falsely or incorrectly used to justify including a lot of junk variables in a model that aren't really necessary. In addition, you can see here that if I run a model, this is the exact same model, except I've changed how y is generated. I've reduced the error from a standard deviation of 6 to a standard deviation of 2. So this is just compressing the error in the model, or in the data generating process down a bit. You can see that my R squared jumps to 96.95%. Now this model is intrinsically, this model here that I've run on this new data set is no different or no better in any way than the model I ran on the previous data set that had the greater deviation in the data generating process. But here, my R squared was, it's 80% or 76, whatever it was before. Now it's 97, 96, 97%. Nothing's different except the fact that the data generating process itself, nature, is just not as noisy. So comparing these two cases wouldn't be very helpful. It's not that one model is better than the other, because the data generating process is just more noisy in the second case than in the first case. So R squared and sum squared errors sort of have issues, and we can address some of those with cross-validation. So what I'm going to do is show you how to execute cross-validation in a sample data set. So what I'm going to do is clear out my memory and draw a couple of variables. And I'm going to construct from the uniform distribution between -10 and 10. And I'm going to draw a y variable that's related to x and z. It's 2x plus z plus 3 plus a randomly distributed normal error term. And I'm going to construct a data frame called sample.dat. And I'm going to do this because the cross-validation package needs the data to be stored in a data frame. All you do to construct a data frame is just use the data.frame command and throw in all the variables separated by commas. And now if you view that data set, you'll see you have a nice data set with y, x, and z all stored up there real nice. And I'm going to estimate 3 models, okay, on this sample data set. I'm going to estimate first a model just between y and x. Then I'm going to estimate a model between x, y, and z, or y using x and z as predictors. Then finally, I'm going to produce a model with x, z, and x times z, an interaction term between x and z as predictors. So if I do a summary of that third linear model here, you'll see that I've got x, z, and x times z as predictors. This is an interaction term which you've probably learned about in your previous classes. So what I want to do is ask, okay, is the first model or is the second model an improvement on the first model? And the answer should be yes, because z is a variable that's in the data generating process. It's relevant. And then I want to ask, is the interaction term relevant? Is that something I should add? And the answer should be no, because that interaction term is not in the data generating process. So how do we do this? Well, what we can do is, the first thing I can do, let's just try the, we can try using the R squared statistics to see if that works. Oops, it's not linear model 1, it's linear model. Oops. Well, the R squared of the linear model is with just x is, let's see. This is executed by a GLM, so we would need to, yeah. So interestingly, the summary of the GLM does not produce the R squared statistic, which is kind of odd, but we could easily do that like this. Y is x. The R squared statistic is 73.39%. Well, okay, that's fine. Let's see if adding z to the model improves. X plus z. 84.7, yes, the R squared says that's better. Now let's see if adding x times z, the interaction term, improves on the model. 85.04, so it's statistically insignificant, although I notice it's not too far from conventional levels of statistical significance. And the R squared says it's better, so we're getting a bad answer from R squared. Cross-validation might help. So the way cross-validation works is, in R, is you go into the boot library here, so if you don't have it already, install it, and if you do, go ahead and load it up. You use the command cv.glm to calculate the cross-validation statistic as I just described in the notebook a second ago, for the particular model you're interested in. So cv.glm is the command. You tell it the data that you're fitting, and you also tell it the model that you wish to draw on, and we're going to use linear model. This has to be a GLM, by the way. It cannot be a an LM. This is why I originally fitted the GLM models. And I'm going to store that in just an object called cv.linear.model. And what I want out of this cv.linear.model has a bunch of different things in it. In fact, if I type this out, you'll see it produces a bunch of objects, a k, a delta, and a bunch of seed values. The delta is what's important. So if I do cv linear model $delta, I get the cross-validation statistic out of this particular procedure. And this is a vector of length 2, and so you might be saying, well, why are there 2 statistics? That doesn't really make sense. Well, if you go into the documentation, which you, cv.glm, you'll see that the delta product, the first component is just the raw estimate of prediction error. That's what I described in the notes. So that's this number right here. The second number is adjusted for the fact that this is actually an approximation to that procedure that's computationally quicker. So if you want to use the adjusted figure, you can. That makes perfect sense to me. So we'll say the cross-validation error in this particular model is 62.96. Now what I want to do is repeat this process for the other 2 models, one of which includes x and z, and one of which includes x, z, and x times z. What you can see is, including z makes the cross-validation prediction error go way down. Our sum of squared errors in this case is far smaller than it was before. But then our prediction error goes up again when we add the irrelevant term xz. So what the cross-validation statistic is telling us is, adding z to the model makes things better, reduces prediction error. Lower is better, lower error is better. Putting x times z, the interaction term, in doesn't really help and actually makes things a little bit worse. So the cross-validation statistic gives us the right answer. It tells us that, hey, probably you should put in x and z, but you shouldn't put in x times z. So that's good news. I do want to point out, though, that these are not infallible processes. So I'm going to redo everything I've just done. The only thing I'm going to do differently is I'm going to change my seed from this number to a different number. So I'm just basically changing the random numbers I'm using to create my data set. And I'm going to just rerun everything and see what happens. Well, now it's telling me that the third model, which has x times z in it, is actually better than the model with just x and z. Because you can see right here, the prediction error is actually lower. So cross-validation is a very good technique, but it's not always a perfect technique. Now, the difference between 40 and 39 is pretty small, and maybe we could say, oh, there's not really much difference here, so the z term is probably irrelevant. Maybe that's true, but nevertheless, it is telling us it's better. So this kind of raises the question, how well does cross-validation work in arbitrary circumstances? And the reason I'm highlighting this is because this is exactly the kind of question that one would answer with the second technique that I referred to in the beginning of this lecture. This is a question of how well does cross-validation work in general, not how well does cross-validation, not what does cross-validation tell me in this data set, it's how does cross-validation work in all data sets, or in general, in expectation. So if I wanted to figure out how well cross-validation worked, I might have to do some kind of Monte Carlo simulation. And we'll actually talk about how we would think about that problem in a few minutes when we get to that portion of the lecture. So sometimes you don't want to go through the computational complexity of fitting a cross-validation statistic. But there's another way of assessing the fit of a model and preventing overfitting, and that's to penalize an existing fit statistic like the R-squared or likelihood, log likelihood. Penalize it for the complexity of the model. Now remember, the problem with overfitting, or a problem with overfitting, is when a model gets more and more complicated, it can improve the fit of the model in a spurious way. So for example, adding a bunch of junk terms to a regression does make the R-squared bigger, even if those parameters, those terms, like those z's in the Monte Carlo simulation we just ran, or in the R simulation we just ran, even if they have nothing to do with y, they still make the R-squared bigger. So what these statistics I'm about to tell you about try to do is to lower the fit statistic according to how complicated the model you're fitting is. For example, how many terms or how many variables are in that model. And so the most basic one of these is the adjusted R squared, sometimes called R bar, written as R bar squared. And R bar squared just penalizes the standard R squared statistic right here with this factor right here, n over 1 minus, or divided by n minus k minus 1. So this is the deflation factor. And what you can see happens is, so 1 minus r squared is the proportion of error, or I'm sorry, the proportion of variance that is not explained by the model. And as k, which is the number of terms in the model, so the number of variables, this is k is the number of variables, and that actually includes the constant, including the constant. As you add more and more variables to a model, k gets bigger and bigger and bigger, which makes this denominator get bigger and bigger and bigger, which makes this whole term, it makes k get bigger and bigger and bigger, which makes the denominator get smaller, because k is subtracted here. That makes this whole term get bigger, which means that this term right here, so let me change colors here, this term right here, which is the proportion of the variance in y not explained by the model, this gets bigger as k gets bigger. So the whole idea here is just to say, well, the more variables we drop into a model, the more we're going to force the model to do that much better in predicting y, in order to say that that term in the model is worthwhile. If you just add in a bunch of junk statistics or junk variables to a model, they may do a little better, but they won't do better, and they may fit the model a little better, but they won't fit the model better enough to overcome this this inflation factor, which is the reason we put it on there. There are also information criteria type statistics, and I've listed two of them here. One of them is Akaiki's information criteria. Let me erase that. And the other is the so-called Bayesian information criteria, or the Schwartz information criteria. And you can see that these are both based on the likelihood of the model, the log likelihood. Here's the likelihood right here, 2ln and what they do is just add to the log likelihood a penalty factor. The Akaiki information criterion, or AIC, adds 2 times k, where k is the number of variables in the model. The Bayesian information criterion adds k times the log of the number of observations. And in both cases, as k gets bigger, the AIC or BIC gets bigger. So in the case of the adjusted R squared, because it's related to R squared, larger is better. We want to explain more variance. But the AIC and BIC have smaller is better, because more likelihood is better, but the likelihood is being subtracted here. So we want that number to be more negative, smaller. K makes it bigger. So these information criteria statistics basically operate in a similar way as the adjusted R squared. They just say, here's the raw fit statistic, the likelihood in this case, and if you add terms to a model, we're going to inflate the, in this case, we're going to make the likelihood look worse by just adding a fixed term in. Now, both the AIC and the BIC have theoretical characteristics, which I'm not going to prove to you. One of the interesting characteristics of the AIC, however, which I'll just note, is that it's asymptotically equivalent to leave one out cross-validation in a lot of models, including the linear model. So as the number of observations goes to infinity, the AIC is the same thing as cross-validation leaving out 1. So in other words, you'll always get the cross-validation statistic will always select the same model as the AIC as the number of observations goes to infinity. This is really nice because the AIC it doesn't have to be calculated n many times. It can be, in fact, you already will have the log likelihood as a result of fitting a model, so you can use the products that you've already made in your model fit process to produce a fit statistic, which is really very useful and related to this cross-validation statistic, which is comparatively harder to produce. There are justifications for the Bayesian information criteria that one could discuss. But one thing it's kind of interesting to point out is that, if I recall correctly, typically the Bayesian information criterion tends to be that they tend to have different. They tend to be harder or less hard on model complexity compared to each other. So, for example, you can see that the slope on K and the Ikaike information criterion is 2. Every increase in K causes a doubling. Whereas the Bayesian information criterion, the slope is ln n times k. I'm sorry, ln n. It's ln n. And so if n is bigger than a very, very small number, that slope is going to be harder. So the Bayesian information criterion is, typically speaking, going to be harder on. It's going to favor parsimony in models more than the AIC in general. One thing that's nice about the AIC and BIC is that you can compare non-nested models, which is to say models that contain different terms on the right-hand side, or that even have different structures on the right-hand side, as long as they're all estimated on the same dependent variable data. In your linear models class, you might have covered the F statistic, which is also a model comparison statistic. But the F statistic has a disadvantage of requiring, in general, that models be nested. So, for example, if I'm going to compare this model to something, it has to include all of the elements of that model and additional stuff. So I could compare these two models fine because everything in here is contained in here. But I could not compare this model to this model because they're not nested in one another. This component of this model is nowhere included in that model. The AIC and BIC don't have that disadvantage. As long as the data set is the same, in other words, as long as Y is the same, I can compare any two models and tell you which one is a better fit to the data set, and the comparison is perfectly valid. So now let's go to R and see how we would implement these tests. The AIC and the BIC are really, really easy to implement in R. And what I'm going to do is just draw a fake data set here, as usual, using x, z, and a y. And you can see y is 2x plus z plus a constant of 3 plus a random normally distributed error term. And I'm going to compute my models again, just like I did in the last demonstration. I'm going to have one model that just has x, one model that has x and z, and one model that has x, z, and x times z all in it. And all I need to do in order to compute the AIC and BIC is just feed that linear model object right into a function called AIC or BIC. So, for example, if I just throw those in there, what this is telling me is that the AIC is lowest for the second model. That's the model that contains x and z. That's good news. That's the right answer. X times z is not a relevant term. As you can see from when we created this data right here, there's no x times z interaction in there, so it shouldn't be there. And the AIC tells us it shouldn't be there, which is good news. The BIC, which as we discussed, is actually harder on additional terms than the AIC. It even more strongly prefers the XZ model. You can see that 643 to 648, that's a bigger absolute gap than the 633 to 635. It's a little dodgy to interpret these numbers as really meaning anything, but anyway. So the BIC tells us the same thing. We shouldn't include x times z in this model, but we should include x and z. That's the right answer. It's a fairly easy thing to use. It doesn't exactly take the place of non-formal diagnostic statistics because AIC and BIC won't tell you necessarily why a model is better. They'll just tell you that a model is better according to a likelihood, according to fit. If you want to know how to improve a model, you're going to have to look more closely at the data. For example, just looking at the linear model BIC of 724.54539 doesn't tell me that I'm missing a variable z. There's no way of my knowing that. It doesn't tell me what's wrong with this model or what's right with it. It's only useful as a comparative statistic once I have an ensemble of models in mind. So now I want to take a little detour and talk about another problem we might find when we're diagnosing model fit problems. And that's the problem of outliers and influential observations. The reason I'm taking this detour is when you conduct, especially when you conduct informal analysis or diagnostics of your models, you can occasionally see that, hey, there's an observation that really changes my fit. And what do I do about that? First of all, how do I know it's a problem? And secondly, what do I do about that? Now, everyone probably in their introductory statistics class does something like the following. You say, okay, I've got an X and a Y here, and I've got some data that I've collected, and one of them is really kind of out there. And when I fit a model to that relationship, I can tell that this observation may be dragging things up a bit. You can see that I'm overestimating all of these different data points. And this outlier seems a bit, it seems different from the rest of the data. And so maybe I should drop it. Maybe I should look into that more. That's a very informal way of looking for outliers and influential observations. And to formalize that slightly, influential observations are ones that are far from the center of the distribution of the independent variable, x in this case, and also have very large error terms. An observation that's far from the median of x but has a small error term like this one right here is not that influential. You could delete it from the data set and it probably wouldn't change the fitted line that much. An observation that has a large error but is far from the line like this one, but is close to the center of x, probably also wouldn't change the fit that much. You could delete it from the data set and it wouldn't really change the slope of that estimated line very much. So you can informally figure out what's going on here, and that's all perfectly reasonable. But I wanted to make you aware that there are also formal diagnostics for identifying influential observations that are discussed in the readings. Two of them are DF fits and DF betas. DF fits and DF betas tell you how much important quantities change when you delete a particular observation. DF fits tells you how much does a particular observation's fitted value change when you don't include that observation in the fit. So for example, if I'm going up to my drawing thing here, suppose I have some data and I've got my outlier here and I fit my line. DF fits asks, okay, if I include this crazy observation in the line or in the model, I get this. If I don't include it in the line, I get this. Where am I here? Yeah, I don't like the gray. Let's do green. So the DF fit statistic says, well, here's my fitted, let me get to red here. Here's my fitted y hat when I include that observation. Here it is when I don't. And so DF fits assesses how big is that gap? How big is the gap in fit when I include or don't include a particular observation in the data set? So in other words, how influential is an observation on its own fit? That's the fundamental question. And DF fits is actually standardized in the sense that this gap is divided by I think it's either the variance or standard deviation. I think it's the standard error of y hat I. So you basically standardize these deviations so that they're in terms of its own standard deviation as opposed to raw variance. DF betas is related, a little different. DF betas, instead of asking about this gap, it asks how much do the beta coefficients change when a particular observation is deleted. So if we go back to our plot here, and we've got x and we've got y, when I include an observation in, I get this blue beta hat, that's the slope of that blue line. When I exclude it, I get the green beta hat. And DF betas asks, what's the difference between these two betas? If I were to take the blue beta hat minus the green beta hat, and then I standardize this according to I think it's the standard error of beta hat, what do I get? How much does this change the slope of beta? The point of this formalized statistic is that it provides you a nice way of getting a numerical grasp on exactly how influential an observation is. And in R here, I want to show you how I might go about this. I'm going to use that grad happiness data set that we talked about a little earlier. I already showed you the linear model between happiness and years is really, it's bad because, as we saw, there's a nonlinear relationship between years in graduate school and happiness. It's a wavy line. I can tell you, I can diagnose that there are problems with this data set in part by looking at the DF fits and DF betas of some of these models. And in particular, I want to focus in on the DF betas here. So the DF betas are estimated by a command appropriately called DF betas, and I'm storing that in this DF beta df.bet.lin object. And if I depict dfbet.lin, and actually I'm going to use the head command just to get the first few rows of this. Wait a second. Oh, okay, I misspelled it. dfbet.lin. There we go. Okay. You can see that this is the first 6 observations, and this is how much the beta coefficient changes when I include or exclude those, when I exclude this particular observation. So when I drop the first observation, the intercept goes up by 0.14, and the years variable coefficient drops by 0.11. How much is that in terms of the actual coefficients? Well, if we do a summary of linear model, actually, if we just do, it's linear model, right? So summary linear model. The coefficients are 0.12 for both, pretty close to that. The intercept coefficient is nearly doubling. That's a pretty big change. And the years coefficient is going to 0. So 1 is a very influential observation, that first one. That's something we should keep in mind. So what I'm going to do is actually use this information to produce a visually impactful plot. What I'm going to do is I'm going to, first I'm going to create an order. I'm going to put the DF betas in order of which observations have the biggest effect on the coefficient for years. And so what I've done is use the order command just like I did before, but what I'm ordering is the second column of dfbeta.lin, and I'm setting decreasing equal to true, so the biggest ones come first. You can see that the 44th observation is the most influential one. It causes the coefficient on years to go up by 0.18, which is pretty big. So now what I'm going to do is I'm going to plot grad happiness versus years. I'm going to plot happiness versus years. And I'm going to set the size of the data point, which is set by CEX, to be equal to the DF betas. Now I'm multiplying it by 10 and setting it using the absolute value because I'm looking at the size of the change, not necessarily the direction of the change. And what this is going to do is produce a plot where the size of the circle of the plot point is proportional to how much the estimate changes once I delete that observation. And wouldn't you know it, the most influential observations are the ones at the peaks and crests of the wavy relationship between happiness and years. And that's because you can tell exactly where the line's passing through. It's passing through right about here. If you look at my cursor right there, it's passing through right there. And the most influential observations are the ones that are far from years and also have big errors, like this guy right here or these guys over there. So these DF beta coefficients can help you, first of all, figure out which observations are really making a difference. And you can use this order to sort of zoom in on, okay, well, if I'm looking at this list, I need to look at observations 44, 89, 171. I need to take a close look at those to make sure there's no data coding error or some other kind of problem. These plots also give me a sense of, I can now get a sense of what groups of observations are making a difference and maybe get a handle on what kind of specification error is happening in my data set. The dffits command is very similar. I just executed a dffits command on linear model, and I stored it in df.lin. df.lin is just going to tell me how much each observation's fitted value changes once I exclude that observation. And as you can see, number 1, the fitted value is changing by 0.14 when I drop observation 1. So it's a measure getting at a very similar concept as DF betas. So at this point, everything we've discussed is really about how well a particular model is dealing with a particular data set. And as I noted at the top of the talk, that's not the only question of interest. In fact, typically in this class, what's going to be of greater interest is this estimator good for this particular kind of data set in general? And if I use this estimator in this particular situation, what kind of problems can I expect to encounter? So as an example, earlier we saw that cross-validation in some cases identifies the wrong model as being the best fitting one or the best one for that scenario. And that might naturally lead you to ask, hey, is cross-validation a good screening statistic? Is it good at picking the model that's the best fit or has the right terms in it or is at an appropriate level of complexity? Now, I'm not going to run that particular simulation, although you certainly you could, and in your homework you're going to run some simulations similar in spirit. But what I want to do is talk about how one answers that question. And the tool I'm going to propose for answering these questions is Monte Carlo simulation. The idea behind Monte Carlo simulation is that you create an environment in which you want to test out how a particular technique or estimator is working. And so I'm going to say, okay, I want to figure out how well the linear model does with binary data. So what I say is, okay, I'm going to create a data generating process that makes binary data. I'm going to draw lots and lots of different data sets out of that environment. So I'm going to get like 1,000 binary data sets that I randomly simulated using R or some other statistical package. Then on every one of those fake data sets, I'm going to estimate my model, in this case like a linear model, and then recover the results. Then I'm going to look at my 1,000 estimates. I'm going to say, how well did I do? Did my estimator get the thing I was trying to get, or did it screw it up? And in this case, I can figure out exactly how much I screwed up because I made the data sets. I know the true value that I was aiming for, so I can get an exact measure of how well did my particular estimator do in this environment. And then what I can do is start to change the environment a little bit. So for example, in the binary case, I can crowd all the observations close to the center, or I can spread them out. I can make the slope bigger or smaller. I can start to change what the world looks like, the world that I've created looks like, and then get a sense of how does the estimator do in different situations. And that's going to allow me to hopefully draw some conclusions about when it's okay and when it's not okay to use my estimator in different environments. So, what kind of things might we assess in a Monte Carlo analysis? Well, we might, for example, look at bias, the difference between the known true value of something we're looking at and the estimated value of something we're looking at. So maybe I'm trying to, say, for example, find a marginal effect, assess a marginal effect, or dy dx, a relationship between y and x. Now, because I created the data set, I know exactly what dy dx is. I made it up. I can ask, how well does my model estimate dy dx relative to the true known value. So the bias would just be, in this case, where am I here? The true marginal effect minus my estimate. If I add all those up, I can get the, or I can take the mean, I suppose, sum them all up, and then take the mean, where n is the number of replications. So n is the number of Monte Carlo replications, the number of fake data sets that I used. I can get an estimate of the bias. I might also not just be interested in the sign of the bias, but the gap. How big is the average gap between the estimated quantity and the true quantity? And in order to do that, I would do something like this. The absolute value of the difference between the marginal effect and the estimate. I might be interested in how much variation there is, variance in the estimate. So I might calculate the variance between ME and ME hat as a way of figuring out how much dispersion there is. Am I generally hitting on target every time, or am I unbiased but hitting all over the place? Just as a brief aside, there's a big difference between the following two estimators. You know, imagine I'm trying to estimate some quantity beta, and here's my density. And if I hit it right on target, so this is I'm going to say this is the gap between my estimate and the true value. If I hit it right on target, I'm right at 0. Okay, so I can imagine an estimator, a really good estimator, does something like this. It hits on average right, and it's very narrowly, it has very narrow variance. It doesn't get very wrong. That's very different than this estimator. Now, both are on average correct, but one of them shoots all over the place. It sometimes gets very low values, sometimes gets very high values. On average, it's right, but its accuracy is quite bad. That's also different than something like this. Now, that's not an unbiased estimate. You can see that its average is actually, in this case, positively biased, but it's very low variance. If you had to choose between the red and the green estimators, which would you choose? Well, that's not immediately apparent because while the green one always gets it a little wrong, the red one could get it right, or it could get it very, very wrong. So we might be interested in how the spread in the estimates. We might also be interested in the in-sample variance of the estimator. In other words, what is my estimator telling me about the standard error of my estimate beta hat? For example, one very common thing to do in a Monte Carlo simulation is to construct 95% confidence intervals for each estimate, like, recover the 95% CIs for beta out of a model, and then determine whether those 95% CIs cover the true value 95% of the time. If they cover it, 60% of the time, what that's telling you is that your confidence intervals are either too narrow, well, they're probably too narrow, and or they're centered around the wrong quantity. Finally, a lot of Monte Carlo estimates assess the root mean square error, which is just if I'm estimating a quantity p, the root mean square error takes my estimate for p for each one of my bootstrap replicates, subtracts it from the true known value that I created in my data generating process, adds up all the squared values, finds the mean, so divide by the number of replicates n, that's right here, and then take the square root. This is a holistic measure of the average deviation between an estimate and a true value. So in particular, it's just a common way of assessing in general how well or badly am I hitting the target in terms of a combination of bias and variance with my particular estimator. And lower root mean square error is better because that means in general, on average, my error is smaller. I'm hitting I am getting closer, both in a variance and a bias sense, to the quantity I'm targeting. So now the question becomes, how do I assess this? in R? How do I actually do this in an applied situation? So let's go to R and see how this might be done. Okay, so now what I'm going to do is show you how to run a basic Monte Carlo simulation. And the question we're going to ask in this case is, and I think this is actually in the notes, is it harmful to include irrelevant variables in a regression in order to stave off omitted variable bias? So lots of regression teachers, and including me at some point, have said something like, hey, if you're on the fence about whether to include a variable in a model, go ahead and include it because it's better to put one in that you don't need than to leave one out than you do, okay, that you do. But some recent research has undermined this advice, particularly some research by Kevin Clark and some of his collaborators. And I want to show you a little Monte Carlo simulation that lays out some of the trade-offs that are involved in this choice. And you're going to finish up, you're going to expand on this analysis in your homework project. So what I'm going to do is empty out my workspace, set the random seed to some number, and then load up the mass library, which I'm going to need for some stuff. And here's what I'm going to do. I'm going to drop down a little bit here and show you exactly what the simulation does. This is the core of my simulation. It's this for loop. So I'm going to do this 1,000 times. I'm going to run 1,000 Monte Carlo replicates. And each one of these, I'm going to draw x out of the multivariate normal distribution, MBR norm. That's why I need the mass library. The mass library has this MBR norm. And I'm going to draw each variable with a mean of 10 and a correlation or a covariance of R. So these are going to be both variables are going to have a variance of 1 and a covariance of R. And I've actually set R up here to be 0.04. Okay. So what this is going to do is, in other words, to draw two independent variables that are correlated with each other through the normal distribution. Then I'm going to say, okay, y is just a function of x. Y is 1x plus a randomly distributed error term. And my sample size is going to be 500. You can see I'm drawing 500 replicates and I'm making 500 y. So the sample size is 500. I'm going to run a linear model including not only x, which is this first bit here, but also z, which is an irrelevant variable that's correlated with x, because I made it so. And I'm going to see what happens. I'm going to store two things. First, I'm going to store the coefficient on x that comes out of this linear model. And I'm also going to store the confidence interval around that coefficient that I get out of the linear model. I'm going to do that with the coefficients and confint functions, okay? Then I'm going to do the same thing again, all the same stuff, but I'm going to omit the relevant variable x. I'm sorry, said that wrong. I'm going to omit the irrelevant variable z, and I'm going to save the coefficient on x, and I'm going to save the coefficient on, the confidence interval around that. So let me just, I'm going to set I equal to 1 and just walk you through one particular iteration of this. So I draw my data set right here, and you can see if I do a plot of, whoops, that's terrible, do a plot of x against z, these things are correlated with each other. In fact, they're correlated, I think, at 0.4. That would be the correlation coefficient. I'm going to draw my y, and I'm going to run a linear model with x and z as predictors. Now, here's what the coefficients vector looks like. And you'll notice if I do a summary of the linear model, that's just the, let's go up here, that's these three estimates right here. 0.23, 0.23, 0.90, 0.90, 0.11, 0.11. So that's just the coefficients. I want the second one, the one having to do with x. So that's why I use that bracket there. And I'm going to save that into a vector called xcoef. That's going to be the ith member, because I'm doing this 1,000 times, remember. And I just created that xcoef vector up here. I just left it empty, so I had somewhere to put it when I was down here. Now here's the confidence interval object, and you can see if I run this, what do I get? Bam. I get 95% confidence intervals around each one of my coefficient estimates. So the confidence interval around z for this particular run is 0.77 to 0.10. That's actually, or I'm sorry, 1.0. That's pretty good because it includes the true value of 1 inside of it. So that's actually good news. I'm going to save that in x.ci, which is a matrix that I created up here specifically for that purpose. And then I'm going to do this all again with the linear model excluding z. So it's the same stuff, I'm just excluding the irrelevant variable. Okay? I'm going to do it 1,000 times. Now you can see the set progress bar thing here, and there's this PB thing up here too. You can look those up in your help functions. I don't want to go into too much what they are, but they basically are just going to allow me to get a visual representation of the fact that this Monte Carlo simulation is proceeding. So in other words, when I execute the simulation, that bar that's now crawling its way across my screen, that's that text progress bar. So it allows me to see if my Monte Carlo has crashed or has hung up or my computer has screwed itself over or something. That's just a nice little feedback thing. You just have to remember to close that progress bar at the end of your simulation, otherwise it'll be floating around in memory. Okay, so now I've got a couple of different matrices. I've got x.ci, which is 1,000 confidence intervals around the coefficient on x for the model that includes z. And I've got x.ci.2, which is without z. Simple enough. And they're executed on the same data set. At each iteration, the two models are run on the same data set, which is actually important for it to be a fair comparison. So what I'm going to do is use a function called call means. That's going to tell me what the average lower and upper bound for the confidence interval was with and without the z variable. So on average, with the z variable, my confidence interval was between 0.858 and 1.146. With the without the z variable, it was 0.87, 1.13. It shrank. The confidence intervals are narrower, and they're still centered on 1, which is the true value. That's really bad news for including irrelevant variables. It's making our inferences worse by making our confidence intervals wider. Our variances are too big. We're getting too much variation in the estimate. I'm also going to do a little plot here. This is x coef. Remember, this is the coefficient for x that we estimated for the model including z. And I'm going to color that in yellow. You can see I've got some variation in what that looks like. What I'm going to do now is I'm going to, right over top of that, I'm going to plot the histogram without z. And you can see I've used the add t option, which is going to add this histogram to the previous histogram, so it's going to plot it right on top. And for the color, I've specified this is RGB, so that's red, green, and blue. This is going to be a blue histogram. And this last element, so it's red, green, blue, something, that something is transparency. So I'm going to make this 0.05 transparent, so it's going to be somewhat transparent. So I'm going to get some color in between when I plot this on top. Now, what am I seeing here? So the gray is the overlapping frequency. If you see yellow, what that means is that the model with z produced more estimates in that range. If you see blue, that means the model without z produced more estimates in that range. And what I'm seeing is that both are unbiased, but the model with z tends to produce more estimates that are clustered around 1, whereas the model the model without z produces estimates that are clustered around 1, whereas the model with z tends to produce more estimates that are further away. So again, we're getting this idea of more dispersion in the performance of the estimator. It hits on target, but it's less accurate. So what this is telling me is including irrelevant crap in a model is not without cost. In any particular data set, in any particular instantiation, I may get a worse answer because I included irrelevant crap. On average, in 1,000 data sets, it'll still hit the target, but on any particular shot, it might miss. It might miss by more if I include more irrelevant variables. And you can probably get this to get even worse if you start adding more and more and more irrelevant variables, or if you change the correlation and all these other things. And that's what you're going to explore in the homework is, how does this problem get worse or better as the situation changes? So it's a really powerful technique. And the reason I'm sort of hitting it hard in terms of teaching it in this particular lecture is, first of all, when we assess how Bayesian or nonparametric models do in the future, we're often going to compare them to structural models, and we're going to ask, is this better than a structural model? How much and why? And we're going to answer those questions with Monte Carlo simulations. But also, and more importantly, more generally for your career, you're going to often probably run into situations where you're going to have a data set. It's not exactly going to match the situation that was envisioned in the model you're thinking about running. For example, you might say, well, I've got this model that's designed for over-dispersed count data, but it doesn't include hierarchy. Is it okay to just neglect the hierarchy? Whatever. You can answer that question, at least inside certain boundaries established by your simulation, with Monte Carlo. I can say, well, let's see what happens if I run 1,000 models on 1,000 data sets with this, and see if it messes up, or see if it does okay. And I can control the environment in which I'm running that and running those simulations, so I can sort of adjust the environment to see, well, how does the situation actually impact the performance of the estimator? So it's a really good, important, practical tool what's good to have in your toolkit, because not every question in statistics has been answered. Not every question in statistics is going to be answered in terms of small day-to-day peculiarities of data sets. And this is a way of empowering you to answer those questions yourself with simulation. All right, that's it for this week. Thanks for tuning in, and I will see you next week.